Welcome back to differential equations. In this video, I want to talk about the Heaviside function. The Heaviside function is a relatively simple piecewise defined function. Let me get my head out of the way and just write out. We're going to generally represent the Heaviside function using the letter u. And let's look at the simplest case. U of t is going to be equal to 0 if t is less than 0, and it's going to be equal to 1 if t is greater than 0. We can graph this function. That's not a u. That's a u. And the graph is fairly straightforward. This is one of those cases where the name was just too good. It took me years to realize that this is not saying that there is a side that is heavy and a side that is not heavy in the graph. The function is named after mathematician Oliver Heaviside, who was also, if I remember correctly, fairly involved in the development of thermodynamics. But the Heaviside function, sometimes called the unit step function, just gives us this two-level effect. We're generally going to see it, instead of just being evaluated as it is, we are most often going to be evaluating u of t minus c for some constant c. Well, changing the argument of the function doesn't change the value of the two cases. It's either going to be 0 or 1, but it does change the inequality. Instead of t less than 0, we have t minus c less than 0. And adding c to both sides of that gives me just that t is less than c. And likewise, the second case is going to be when t is greater than c. Depending on your sources, you'll see a couple of variations of the Heaviside function. First of all, as I write it, the Heaviside function is defined for all real numbers. It's very often defined so that t minus c can take on a range of values, but t itself must be bigger than 0. That definition is just because the Laplace transform doesn't behave well around negative values. The other thing that you'll often see, my function is not defined at 0, or when t is equal to c for the second case. Sometimes you'll see the Heaviside function with one or the other endpoint being defined. We're going to use the Heaviside function inside of integrals, inside of evaluating Laplace transforms. And one of the things that you learned in an integral is that it doesn't matter if you are integrating on an open interval or a closed interval. It doesn't matter if the boundary points are included in the interval or not. It doesn't change the integral. And so for that reason, I just don't care. I don't care if this is defined to be equal to 0 when t is equal to c, if it's defined to be equal to 1 when t is equal to c, or if it's defined to be randomly 5,000 when t is equal to c. That won't change anything at all, and I don't have to think about it this way, so I don't. All right. This is going to be a powerful tool to extend the types of functions we can handle in a non-homogeneous second-order linear ordinary differential equation with constant coefficients. And we're going to do that extension using the Laplace transform. So the first thing I want to do is evaluate the Laplace transform. And we will see that the Heaviside function is very rarely used on its own. Generally, we will have some other function f, also evaluated at t minus c, times our step function u, evaluated at t minus c. And to figure out what happens here, we can set up the integral. Right? The Laplace transform is always the integral from 0 to infinity of e to the minus st times our function, in this case, f of t minus c times u of t minus c dt. You've seen in calculus that whenever you want to evaluate an integral on a piecewise defined function, you need to split the integral up and look at each piece separately. So my function u splits when t is equal to c. So I'll still get the integral from 0 to c of e to the minus st times f of t minus c, and u of t minus c, whenever t is between 0 and c, is equal to 0. And of course, evaluating a function or integrating a function which is 0 just still gives you 0, so we can ignore that term entirely. And then we'll have the integral from c to infinity of e to the minus st times f of t minus c times u. But the Heaviside function between c and infinity always has the value of 1. So we are looking at the integral from c to infinity of e to the minus st times f of t minus c dt. This is a little bit messy. In order to figure out what to do here, I'm going to do a fairly straightforward u substitution. Right, this gets a little bit confusing. I have a capital U and a lowercase u going on in the same problem, but the capital U is kind of gone, so I'm not that worried about it. It turns out that if I let u equal t minus c, some good things are going to happen. Of course, du is equal to dt because c is a constant. And when t is equal to c, u is equal to 0. When t is equal to infinity, u is equal to infinity. And so this change of variables is going to give me the integral u goes from 0 to infinity of e to the minus s times, well, it was t, but if u is t minus c, then t is u plus c. Then f of t minus c becomes f of u, dt becomes du, and we're more or less happy. Playing around a little bit with properties of exponents, e to the, actually let's come off to the side so we don't have to write the whole thing out. E to the minus s times u plus c is e to the minus su minus sc, which I can write separately as e to the minus sc, e to the minus su. And the reason I care about that is e to the minus sc is constant with respect to u, so I can factor it out of the integral. I'm going to have e to the minus sc outside of the integral, and then the integral from 0 to infinity of e to the minus su f of u du. It looks a little bit weird because it's u instead of t, but because we are integrating over u, we don't really care what variable we use. It's a dummy variable telling us where we're plugging things in. We're plugging things in here, and we're plugging things in here. And the thing is now called u instead of t, but that doesn't matter. This is the Laplace transform of f of t. So we've got e to the minus sc times the Laplace transform of f of t. This is going to be very useful to us in both directions. We're going to very frequently be happy that we have a way of taking a Laplace transform of a function that involves a Heaviside function, and we're going to be very happy that we have a way to deal with e to the minus sc for some constant c when we are taking a Laplace transform. All right, let me write this whole thing all in one line. The Laplace transform of f of t minus c times the Heaviside function u of t minus c is equal to e to the minus sc times the Laplace transform of f of t. This is one more case that should go on your list of Laplace transforms. We will be able to use this to our advantage in the very near future. All right. That takes us to a fairly standard, come on, there we go. That takes us to the question that we asked from the beginning: why is the Heaviside function useful? It's a piecewise-defined function, but it's an incredibly simple piecewise-defined function. That's exactly why it is so useful. Because of how simple the Heaviside function is, we can use it to model any sort of piecewise-defined function. Or, to put it another way, we can take any piecewise-defined function and rewrite it as a sequence of Heaviside functions multiplied by some constant. And that's how we're going to use it to our advantage. If we're solving a differential equation where the right-hand side, the driving function, is a piecewise-defined function, for example, y prime plus y is equal to the piecewise-defined function 0 if t is between 0 and pi, 3 cosine t if t is greater than pi, along with the initial condition, say y of 0 equals 5. This is a first-order linear homogeneous ordinary differential equation with constant coefficients. We could solve this one using the method of integrating factors, but I want to use this as a tool to build up. If we had a second order or a higher order differential equation, this would be a little bit messier. So let's look at the simple example. And the first thing I want to do is take this right-hand side and rewrite it using a Heaviside function. In this particular case, that's not going to be all that bad. Instead of 0 and 1, it's 0 and 3 cosine of t. And it turns on when t is equal to pi. So we want this to be 3 times the cosine of t times the Heaviside function of t minus pi. That will give us the Heaviside function is 1 whenever t is bigger than pi, and 1 times anything is that thing. Whenever t is less than pi, this will give us 0. That's exactly what the piecewise-defined function does. Up next, we are going to want to take the Laplace transform of this function, which is, well, we have a formula, but this doesn't quite fit into the formula. What we want is 3 times the cosine of t minus pi times u of t minus pi. I can't just arbitrarily subtract pi from a trig function, can I? This is an identity in trigonometry that we should be familiar with, but if you aren't, I can establish it pretty quickly looking at the graph. Taking sine or cosine and shifting it by exactly pi is the same thing as taking the negative of the original function. So if I take my original function here and I just put a negative in front and hit the right key, come on. Sorry about that. If I just hit that negative, we can see that the functions finally line up and everything works out. Or if I put the negative in the other place, then I could take the situation I have and write it in a form that everything is going to work. Now I can take the Laplace transform. The Laplace transform of y prime plus the Laplace transform of y should be equal to -3 times the Laplace transform of cosine of t minus pi times u of t minus pi. Using the tools that we've talked about previously, the Laplace transform of y prime is going to be s times the Laplace transform of y minus y of 0. And then we have the Laplace transform of y. And using the tools that we just developed, the Laplace transform of cosine of t minus pi times u of t minus pi is going to be e to the minus pi times s times the Laplace transform of cosine of t. Continuing on from here, our initial condition was that y of 0 is equal to 5. And the Laplace transform of cosine of t is s over s squared plus 1, right? K equals 1. Generally, it's s over s squared plus k squared. Right. Rearranging a little bit to solve for L of y, we'll have 5 over s plus 1, and we will have -3 times s over s plus 1 s squared plus 1 times e to the minus pi s. This first piece is fairly straightforward to deal with, so I'm not even going to worry about thinking about it. This piece is an annoyance. Unfortunately, the only thing that we have at our disposal is partial fraction decomposition. S over s plus 1 times s squared plus 1 has to be equal to some constant a over s plus 1 plus some linear factor bs plus c over s squared plus 1, which means that s is equal to a times s squared plus 1 plus bs plus c times s plus 1. And if we expand all this out, and group things together. We get the system of equations 0 equals a plus b, 1 equals b plus c, and 0 equals a plus c. That first equation pretty quickly gives us that b is the opposite of a. The third equation pretty quickly gives us that c is the opposite of a. And so by merging these together, we get that b must be equal to c. Then 1 is equal to b plus b, or 2b, which means that 1/2 is the value of b. And if b is equal to c, that means that 1/2 is the value of c. And if a is the opposite of either of those, that means that negative 1/2 is a. We can plug all of that back into our equation, and we get 5 over s plus 1 stays the same, minus 3 stays the same. That fraction gets expanded out as negative 1/2 over s plus 1 plus 1/2 s plus 1/2 over s squared plus 1, and that's all being multiplied by e to the minus pi s. All right. Cleaning this up a little bit to make our lives easier. We've got 5 over s plus 1. We've got plus 3/2, 1 over s plus 1 e to the minus pi s. We've got minus 3/2 s over s squared plus 1 e to the minus pi s. We've got minus 3/2 1 over s squared plus 1 e to the minus pi s. And so y itself is the inverse Laplace transform of this. So we'll have 5 times the inverse Laplace transform of 1 over s plus 1. We will have 3/2 times the inverse Laplace transform of 1 over s plus 1 times e to the minus pi s. We will have minus 3/2 times the inverse Laplace transform of s over s squared plus 1 times e to the minus pi s. And we'll have minus 3/2 times the inverse Laplace transform of 1 over s squared plus 1 times e to the minus pi s. The first term here is just an exponential. 1 over s minus alpha becomes e to the alpha x. So in this case, alpha is negative 1. So we'll have y is 5 times e to the minus t. Then we'll have 3/2. Inverse Laplace transform of s plus 1 is still e to the minus t, but it's being multiplied by this exponential. And those exponentials drive Heaviside expressions. So this is going to be e to the minus t minus pi times the Heaviside function of t minus pi. The same thing is going to happen. S over s squared plus 1 is cosine. In this case, it's going to be cosine of t minus pi times the Heaviside function of t minus pi. And then 1 over s squared plus 1 is usually sine, but in this case, because of the exponential, it's going to be sine of t minus pi times the Heaviside function, that's not a u, Heaviside function of t minus pi. Remembering what we talked about before, cosine of t minus pi is just the opposite of cosine of t. Sine of t minus pi is just the opposite of sine of t. We've got a whole bunch of 3/2 and a whole bunch of Heaviside functions, so we could clean that up if we want to. 5e to the minus t plus 3/2 times e to the minus t plus pi is just an extra factor of e to the pi. And then we'll have plus cosine of t and plus sine of t, all being multiplied by the Heaviside function at t minus pi. Technically speaking, we are done at that point. But the original problem was given as a piecewise defined function, so that's where I want to end things as well. So we've got a piecewise defined function that is equal to 0 if t is less than pi and is equal to 3/2 times all this stuff, e to the minus t, e to the pi, plus cosine of t plus sine t if t is greater than pi. And I can take this one step further by adding this part in on both of those. So y is equal to a piecewise defined function. 0 plus 5e to the minus t is just 5e to the minus t. Then we have 5e to the minus t plus 3/2 e to the pi. E to the minus t, I guess we could combine some like terms there if we wanted to, but I don't want to. Plus 3/2 cosine of t plus 3/2 sine of t. That really is a long mess, but that's okay. That's just what happens. That's the case when t is bigger than pi. This over here was the case if t is less than pi. And there we have it. It's a mess. It's a bookkeeping nightmare. But we can use the Laplace transform along with the Heaviside function to handle piecewise defined functions as our driving function for a differential equation. Thinking about this in terms of applications, my usual model for a second order differential equation is a mass hanging on a spring. My spring is just out of reach. So let's grab my spring. In this case, I have my spring sitting there. It's just sitting there doing its own thing, which might be nothing, which might be something, I don't know yet. And then after some amount of time, I start shaking the spring. And when I start shaking the spring, it starts bouncing. And maybe after some amount of time, I'll stop shaking the spring and it will keep bouncing until friction causes it to slow down and come to a stop. That's the kind of thing we're looking at when we're talking about a piecewise defined driving function. We can have functions that turn on, we can have motors that turn off, we can have motors that change behavior at some point in a cycle, all based around the mathematics of the Laplace transform combined with the Heaviside function. Solving a differential equation is a lot of time and effort. I want to look at something a little bit simpler just to get you familiar with the idea of the Heaviside function as a way of representing a piecewise defined function. So I want you to consider the function f of t, which is going to be defined piecewise. F of t is equal to 0 if t is less than 3. F of t is going to be equal to the sine of pi t if 3 is less than or equal to t is less than 5. F of t is going to be equal to 2 times the sine of pi t. If 5 is less than or equal to t is less than 6, and then f of t is going to be equal to 0 if t is greater than or equal to 6. This is a very messy piecewise defined function. Again, thinking about it as a motor, we're looking in stages. For the first 3 seconds, the motor is off. Then we turn the motor on for 2 seconds, and then we crank the motor up for 1 second before turning the motor back off. I'll give you the hint that when you're thinking about the Heaviside function, I want you to think about how things are changing. So we have to turn the motor on, we have to add more to the motor, and then we have to take away the power of the motor. But we can write this as the sum of a couple of Heaviside functions. I want you to take a couple of minutes and see if you can reason out how that's going to work. And I'll see you in the next video.